Go ahead.
Hello, everyone. Welcome to the final day of this great workshop. Let's get started straight away with Joel Primack. He's introducing, I think, the title fight, simulations versus observations.
So I'm going to talk about dark matter and use of dark matter to try to explain, to understand better what's going on with hydro simulations and with maybe the real universe. Galaxy morphology, especially focusing on clumps. And at the end, reminding people that today is also the first day of the Assembling Galaxies of Resolved Anatomy, the Agora meeting. Whoops. So astronomy is observations and theory. Observations are snapshots. Theory basically makes metaphorical or real movies that, if we're successful, link together images that represent what the observers see into a coherent picture of how the universe actually evolves. First, I'm going to talk about dark matter simulations, then about hydro simulations. So the paper that Aldo Rodriguez Puebla led, based on the bowl-shaped Planck and multi-dark Planck simulations, which were run and analyzed also by Anatoly Klipin, who's also here. The paper's about to appear in monthly notices. It's accepted. So it's a massive assembly of fitting functions and descriptions of what we found. So there's only a few simulations that are big and represent the Planck cosmological parameters. The main other one is called Nu squared GC. It's a Japanese project, and they've also just posted their semi-analytic model based on it. We have fitting functions for essentially anything you're interested in: halo mass functions, sub-halo mass functions, velocity functions. This is the relationship between the halo mass and the maximum circular velocity. We also have one for the peak circular velocity. Notice that the curves are essentially parallel at higher redshifts, but with a significant zero-point offset. The Planck parameters made a big difference compared to the WMAP parameters in the abundance of halos. So about 30% more halos at most circular velocities and masses at redshift 0, more and more at higher redshifts, and at redshift 8, the abundance of 200 kilometer a second halos, very rare at that redshift, is higher by a factor of 3 when you go to the Planck rather than WMAP 5 cosmology. This is largely because of the increase in omega matter. The halos start earlier, grow faster, and continue to grow longer because matter dominates a little bit longer. Lots of interesting stuff in the paper. I'm just highlighting a few things. This is the Peebles versus the version of the spin parameter that we introduced in the paper that James Bullock led in 2001, the first of his 2 dissertation papers. Notice the strong decrease in the Peebles lambda with increasing redshift, whereas there's no systematic behavior with the Bullock lambda. And this is because of this E, and you can also rephrase this in terms of concentration. So it's important that to notice that they're different. This is a point that several of us have made orally several times during the meeting. And it's something that we've known for a long time. There was a paper that James led in 2000 that I think made this point. Namely, that the abundance of halos at a given circular velocity, say 190 or 100 kilometers a second, hardly changes out to redshift about 4. And even after that, it falls gently. The halos are getting smaller, but they're denser. So they certainly can't host as many stars or even as much baryonic mass. If you'd assumed a Tully-Fisher type relation, you would predict the abundance of stars like one of these curves, depending on exactly what you assume. But the actual abundance looks like this. So it falls very dramatically as you go out in redshift. And the predictions would be already significantly wrong at redshift 1 and at redshift 5 by more than an order of magnitude. So the 0 point in the Tully-Fisher type relations must increase. This is stuff that isn't in that paper. It's in a paper that we're finishing and that should be submitted very soon, being led by my graduate student, Christoph Lee. This is the distribution of densities, smoothed on a scale of 16 megaparsecs, 8 megaparsecs, 4 megaparsecs, 2 megaparsecs, 1 megaparsec, half a megaparsec. We've simply overlaid 1024 cubed cells on many time steps of the Bolshoi-Planck simulation and counted particles and smoothed, and then tagged every single halo with the particle distribution. This is the same information, but now displayed on a logarithmic scale. And the fits are using something called the generalized extreme value distribution. This is how it changes with a smoothing scale of 1 megaparsec from redshift 2, that's the green curve, 1, a half, and 0. Basically, mass moves from low-density regions into high-density regions, and the result is that the low-density regions become still lower density and the high-density regions become still higher density. That's the form of the generalized extreme value distribution. Using these things, one can calculate the mass function in regions of different density, high density, average density, very low density. These are the densities. The green is the lowest 10%, and at different redshifts. A related project that was led by it was actually the senior thesis project for Radu Dragomir, who's been in charge of recording all the videos of the lectures. So he's in the back room now. We showed that abundance matching is essentially independent of density. That is, you do the standard abundance matching where you don't pay attention to density, and then make predictions. And in the R band, they work extremely well. As you go to shorter bands, they don't work so well, which is more or less as expected. This is complicated but interesting. What we've done is to percentilize the distribution of the dark matter halos of different masses, low mass, intermediate mass. This would be centered on 10 to the 12 solar masses, and high mass and basically group mass. And this is how concentration depends on density. Very high in low density and high density regions, and then there's an upturn also in the various low density regions. The spin parameter has an interesting dependence on density. It's lower than average in low density regions. Turns out that's because the halos don't have another nearby halo to torque them up. It's much lower than average also in high density regions. Completely different reason. It's because of stripping. The halos, the low mass halos in high density regions are mostly losing mass because they're within the Hill radius of a nearby more massive halo. And that tends to strip off the high angular momentum material. The mass accretion rate has a pretty smooth dependence on density. In this paper, we explore many, many aspects of the density halo mass relation. This is going to be a related paper. So it turns out that for these low mass halos in dense regions that are stripped, a little bit of stripping and a lot of stripping cause absolutely opposite behavior, both in concentration, spin, also in prolateness and many other things. A little bit of stripping increases the spin and decreases the concentration. A lot of stripping increases the concentration and decreases the spin. We have understood how this happens, and this will all be explained in that paper. If there's time at the end of the talk, you can ask me and I'll tell you. Moving on to the shark idea. So shark is this idea that the stellar star formation rate could be controlled by the halo accretion rate, at least for star-forming galaxies. You can show that this has to be true on average to the extent that the stellar halo mass relation is more or less independent of redshift, which it is more or less. The other key thing you have to know, and everybody should be familiar with this, is the main sequence, that at least at the low mass end, the star formation rate is proportional to mass with a proportionality constant that grows with redshift, out at least to redshift 2.5. So so one of the things that we checked in this paper is, which is an offshoot of the Bolshoi-Planck paper, is that the halo accretion rate is about plus or minus 3 or 0.3 or 0.4 dex, independent of mass and redshift. And dm star dt is dm star dm halo dt, plus the term that depends on the redshift change. To the extent that you can neglect this term, dm star dt is just this first term, which you can write as m star over m vir d log m star d log m vir. This, of course, is the slope on that log plot, dm vir dt. Now, this has to be true on average, to the extent that you can neglect this term. If it's true halo by halo, we call this the shark situation. Halo stellar and halo accretion rate coevolution. So this is what the halo accretion rate looks like, the mass accretion rate. And it implies that on the main sequence, the specific star formation rate depends like this on redshift. You can see it's actually an excellent fit out to redshift 4. The reason we call it shark is partly because we then put the shark in the bathtub. So we do sort of standard bathtub type models, but now we're, in addition to assuming equilibrium, we're actually getting the star formation rate from shark, and then we can predict things like the metallicity evolution. This is the mass loading factor evolution, and we get results that are very consistent with simulations and observations. We need to extend this to higher mass galaxies and take quenching into account. Does it correctly predict the growth rate of central galaxy stellar mass from the accretion rate of their halos? We've started to test this in simulations. These are Daniel Severino's simulations analyzed by Nir Mandelkert. Thanks, Nir. And in many cases, it seems to work remarkably well. There are some interesting failures. Here's a case where the shark prediction in red is much lower than the actual simulation results at late times, although both predicted a sharp decline. And here's a case where the prediction was low at higher redshift, but the star formation rate was high. And a lot of this is due to lumpy accretion. We explained in the shark paper that we're basically assuming smooth accretion. We have to correct for lumpy accretion. So this is an ongoing area of research. Now I want to switch to talking about hydro simulations. Of course, there's a lot of work based on Illustris and Eagle, these low resolution, kiloparsec resolution simulations where everything is tuned. They're basically like semi-analytic models. You can't trust them for what's going on inside the galaxies because they're not really resolving very much, and anyway, it's all been tuned. It's not self-consistent. So here we're going to talk about the high-resolution simulations with resolutions of a few tens of parsecs. The advantages are that they are trying to be more self-consistent, although, of course, a great deal of the relevant physics is sub-grid and is guesswork. But they make all kinds of predictions that can be compared directly with observations, including morphology and spectra. Unfortunately, we can't run statistical samples, at least not yet. So what we have to try to do is understand what's going on in the simulations and abstract those things and maybe put them into semi-analytic models. Two groups that have done a lot of these simulations are the group that uses Anatoly Klipin and Andrei Kravtsev's adaptive refinement tree code, as modified also by Daniel Severino, and the feedback and realistic environment simulations led by Phil Hopkins. And there have been several talks about those also this meeting. So in all of these simulations involving the ART code run by Daniel Severino, we've basically chosen halos that are more or less logarithmically spaced evenly in log mass, which is also log circular velocity. There's high mass ones that we call those generation 1, and there's low mass ones, a set of 35 initial conditions that have now been run 4 times. We call those generations 2 through 5. 2 was supernovae with thermal feedback. 3 added UV radiative feedback and photoionization and so forth. 4 added an infrared boost to the radiative feedback. 5 added supernova pressure feedback, similar to what the fire simulations do. And in the future, we also want to include AGN. These have mostly been run just to redshift 1. So, as you heard from Abishai, they produce compaction, they produce elongated early galaxies in agreement with observations, and they produce clumpy star formation. I'm just going to very quickly go through the first two topics because Abishai reviewed them very well and in some detail yesterday, and then I'll talk a bit about clumps. So there's very strong evidence that galaxies really do go through this blue nugget to red nugget phase. And we see very similar behavior in the simulations. These are simulations of that go through this compact, rapidly star-forming, 5 minutes, I understand, region of the diagram. These are ones that don't, and in the Barrow 2013 paper, we called this the slow track. These are mostly disk galaxies. These are spheroids. This is Abishai's cartoon as to how these things work. There's an annoying delay with this gadget. This is a nice video that Nir made. Sometimes Daniel saves thousands of time steps so we can follow these clumps as they evolve and make these kinds of movies and track the kind of diagram that Abishai showed. And by following the clumps, we've learned a certain amount, which I'll come to in a few minutes. This is the evidence that the low-mass galaxies at redshift 1.5 to 2 are very are very elongated. The axis ratio distribution peaks at about 0.3, and there's very little above about 0.6. And there's no way to understand this except that the galaxies are basically quite elongated. They can't be disks. You'd have a more or less even distribution of axis ratios. They can't be spheroids. That would all be axis ratio near 1. So the simulations as long as the center is dark matter dominated, most of the simulations are quite elongated. As soon as the center becomes star dominated, the simulations become more oblate, as Abishai mentioned yesterday. So nearby galaxies are disks and spheroids, but galaxies start looking like zucchinis. Clumps remain a crucial challenge for simulators. These are pictures of clumpy galaxies from Yiqing Guo's talk at last year's Galaxy Workshop. Yiqing showed that the fraction of clumpy galaxies that have at least 8% of their light, the UV light, coming from a massive clump offset from the center, the fraction is at least 60% at all redshifts down to redshift to half for the lower mass galaxies, and there's a downsizing phenomenon. The higher mass galaxies have a decreasing fraction, but clumps are still quite common. Also, this was the 2012 data, there's a strong dependence of the color of the clumps on their radius from the center, in the sense that as the clumps are seen closer to the center, they're redder, that means they're older, and also probably dustier. And Yiqing gave me a new figure, and you see that this effect is especially prominent at all redshifts, high redshift, low redshift, in the lower mass galaxies, to some extent in the intermediate mass galaxies, not so much in the high mass galaxies. And we're checking to see if the simulations look like that. Everybody else who does such simulations should be checking the same thing. Now, this is a summary from Nir Mandelker's recent paper, and it basically shows very similar behavior. So age increasing as radius decreases, the mass of the clumps, the metallicity, the gas fraction goes down, the star formation rate is constant, but the specific star formation goes down, and the metallicity increases as you go inward. So these should all be compared, but we're certainly seeing a lot of the clumps. The amount of clumps depends strongly on the feedback. This is exactly the same initial conditions run to the same time. This is without the radiative feedback. This is with radiative feedback, generation 2, generation 3. And they're more elongated, and they have fewer small clumps. We did a comparison of those two simulations. This is a paper led by my former student, Chris Moody. And what we found was that the massive clumps above about 10 to the 8 solar masses survive inclusion of radiative feedback and are found in the mock observations. We also showed that there's no one-to-one correspondence between the clumps that you identify in high resolution and the clumps that you identify in what would be seen by HST. let me skip this one. It's complicated. Basically, the point that Avishai is making in this slide and the other slide were that lots of observers are seeing these clumps and are seeing the sorts of trends that I just described. So let me just conclude by reminding you that the Agora project is continuing. There's about 140 participants from 60-plus institutions worldwide as of now. And we're going to be discussing especially an isolated disk, a Milky Way mass disk, and it's been treated by these 9 different codes, 2 versions of ART and ENSO and Ramses, so adaptive mesh refinement codes, and Shanga and Gadget and Gasoline and Gear and Gizmo, which are more following particle treatment of gas. And the interesting result is that the simulations are more sensitive to input physics than to the intrinsic code differences. And we have a number of other projects in the works, and so Agora continues. Thank you, and if there's any time left, I'll be glad to take some questions.
Yep, there's time for questions for Joel. So you stressed that the latter generations of Vela were particularly useful for trying to understand the effect of feedback on the prescriptions that you've made. So we've heard at some level, I guess, 2 or 3 main predictions from this group over the years. One is this kind of compaction in some
elongated galaxies, sense. Clumps.
Fine. The compaction in the clumps always seemed to me to be the ones that I was most worried about feedback being, it being particularly sensitive to feedback. What's the sense of how sensitive those results are to feedback?
Elongation, I don't think very much.
Fine.
Clumps, more feedback destroys or limits the lifetime of the small clumps, but so far it seems to keep the large clumps. But the 2 new versions, generations 4 and 5 is still running. 4 is finished, but not finished being analyzed. So that's going to be a lot of work for the next few months. We've set up, Greg Snyder and Raymond Simons have set up a pipeline to very quickly generate not only many tens of thousands of images from sunrise, degraded to appropriate resolution for HST and JWST and other observations, but also IFU data cubes at the same time. So we're going to be producing vast quantities of output, which we're going to make public actually very quickly. So other people as well as we can compare to observations from all of these simulations. And I think it'll be an interesting test bed to have these different versions of feedback and see just what they're... Also the circumgalactic media. Using the Trident code, which is now part of YT, you can do very realistic quasar absorption line predictions to be compared with the vast amount of data that we now have.
Yeah, on the topic of clumps and the long-lived clumps that you're finding, I'm wondering if you can comment on Antonia Olkopchik's paper with Phil, where they found that the mean lifetimes of clumps were about 20 megayears, and that most of them did not survive very long and did not radiate.
Actually, what the paper says is that the maximum lifetime was 20 megayears. The mean lifetime was less than 10.
No, I'm looking at the abstract. The mean lifetime is 20.
All right. They also didn't find a lot of star formation in the clumps. Those are gas clumps. And Nir Mandelker saw clumps that looked like those, but we don't call those clumps because they don't look like they survive very long. But in any case, as far as I can tell, that one simulation of a relatively low-mass galaxy isn't clumpy, isn't what Yiqing Guo would call clumpy. Well, until we have a representative sample from different groups like the Fire group, we're not going to be able to tell. So later today, Robert Feldman's going to talk about a fairly big sample of simulations of more massive galaxies. And at redshifts above 2, the majority of those should be very clumpy. Are they? We can ask Robert.
It's time for one quick question while the next speaker sets up.
Hi. This is actually more of a comment, if I could just address the previous question. Regarding the results of Okhopchik et al., there were two main differences between that work and the work that we've done. Number one is just basically how they define clumps. They define clumps in a very different way than what we do, which is at least part of the reason for the discrepancy in the results. I can talk a bit more about that offline. The second reason is, of course, the feedback. And in my opinion, the focus of the future research on clumps should really be to constrain the models of stellar feedback, because clumps, and this also addresses your question, are very sensitive to how you implement the feedback. And I think that's a wonderful opportunity if we can compare different simulations with different feedback recipes to the observations as they get more and more detailed about how long clumps survive, clump ages, etc. That will be a wonderful way to constrain different models of stellar feedback, in addition to the standard ways such as the stellar mass to halo mass relation.
Okay, let's just thank Joel one more time.